This is a production of Cornell University.
We're going to start a new section now, okay? And this Unit 3 is really all about management. I'm going to start talking about management by talking about nutrients. Now, the lecture, I mean, you've seen some of these slides. We're going to be talking about nutrient cycling, just sort of to renew you. But actually, you know what? Jean-Marc, can you kill the first bank of lights? I forgot to do that. I apologize. You guys can see that? Cobians? All right. And common conversation. It's, it's essential for our life. All its availability or lack thereof is really controlled by it really controls the distribution of flora and fauna. And in many cases, the distribution of flora and fauna also controls the nutrient cycling. Certainly the nitrogen cycling is a good example of that. Okay? And when we talk about nutrient cycling, we're really talking about these three factors. What's controlling the pools, both the sources and the sinks, and what's the control between them, the fluxes. Okay? So, this is cutting off the screen. We've lost half this, or a chunk of the slide. Yeah, I guess it's okay. And again, you guys have seen this slide as well. The larger sinks of nutrients are generally unavailable to organisms, but there is always a group of organisms that are involved, with the exception of potassium, but potassium is usually not a limiting nutrient, that specialize in operating on this unavailable pool, making it available to everything else. Okay? Much of this transformation, and this is why you're in a soils course, this is why I'm talking about it, much of this transformation is soil related and is controlled by soil characteristics or conditions. So what we're going to do for the next 3 lectures is basically follow this flow chart. We're going to be talking about, again, nutrient cycling, but from a different perspective. We're going to be talking about the management of those nutrients. We're going to be talking about nutrient management specific as well as fertilizers. And then finally, we're going to be talking about environmental dynamics and the quality of the dynamics on those nutrients. Or not just on nutrients, but on other management issues with soils. Okay? Now, the model system that we're going to be operating on is mostly agricultural fields or agricultural crops, whether they're field crops or truck farm type of crops. But keep this in mind when we're talking about forested systems, agricultural systems, as well as grass systems. Okay? We're talking about management of these materials across a lot of different type of plant systems. All right. Now, what we're going to do today is we're going to be talking about nutrient cycling. And when we talk about nutrient cycling and when we talk about nutrient management and fertilizers, which is going to be the next lecture, I want you to keep in mind these 6 things. Now, we've talked about all these. I mean, this is all Unit 1 type of stuff, and some Unit 2. But the first thing I want you guys to think about is the parent material. The texture of this material and the parent material. How is that going to be affecting nutrient dynamics? Okay? Certainly, when you start talking about texture and mineralogy, you're going to start talking about what's in the material as it degrades or weathers and becomes available for nutrients. But also, when we start talking about texture, we also should be talking about surface area. Because remember, the surface area is the edge effect. Everything's going to be happening on that. Okay? Now, the nature between the mineralogy and the texture, you're going to be starting to talk about cation exchange capacity as well as AEC. Okay? And that has to do with that surface and the mineralogy combined. Okay? Also the climate. Climate, for a number of reasons we're going to be talking about. First, climate is going to affect biological activity. But second, climate is also going to affect reaction rates, chemical reaction rates, the C10 rules. And the presence of water allows different reactions or the frequency or the speed of those reactions. Okay? Biology. Obviously, biology has a lot to do with the cycling itself, but also the organic matter as one of the pools. Okay? pH, another really big important one. We just got done talking about pH. pH and its effect on the active acidity pool and its reaction rates with exchange capacity, relationships with soils, but also pH with its effect on solubility of different materials. And then finally, the nutrients themselves. So, the model system we're going to be talking about is an agricultural system, primarily plants. So let's talk a little bit about plants. Plants are made up of basically 75% water, 25% dry matter. Okay? That dry matter is mostly CHO. You guys have seen my CH2O slide all the time, basically representing organic matter. This is the reason why we use that. Okay? The nutrients, we call them essential nutrients. Essential nutrients basically are those elements that are necessary for the plant to complete its life cycle. That doesn't just mean grow, but it also means to make seeds or reproduce. Each essential nutrient, and this is why they're essential, has at least one function in that plant, or in us for that matter, for which no other nutrient can substitute. That is why it's called an essential nutrient. When I was in grade school, I learned this as C. Hopkins Cafe. Those were basically the macronutrients versus micronutrients. There are macronutrients versus micronutrients. Macronutrients mean basically there's an abundance. I learned it as C. Hopkins Cafe. That was the mnemonic that we used. But you can't use Fe anymore. Fe is not considered a macronutrient, and Mg is now considered a micronutrient. Whatever. But the important note here is that there are some of these nutrients that we need a lot of it, and some of them we need very little bit, a trace amount of it. Okay? Some plant species also need sodium and silica. Silica is a big one for grassy type of materials, grass plants, because they need it actually for their structure to keep them upright. Okay? And then there are also the legumes, which basically those organisms that are doing the symbiotic nitrogen fixation. Those guys need to have cobalt. Okay? But the rest of us don't need that, and most plants don't need that as well. All right. Now, I talked earlier in this semester about the barrel analogy, and I want to use this analogy one more time to sort of get us into the flow of what this lecture is about. Okay? You guys remember what the barrel analogy is? Okay? The idea here is that the barrel represents the potential growth for something. And we're going to be talking about plants, so it's the potential growth for plants. Okay? And each stave in the barrel represents a supply of something that plant needs to reach its optimum growth. Now, the reality is the plant will never get larger than the barrel. That's its optimum potential. But it certainly can grow smaller than that barrel based upon limitations on its growth. In this scenario right here, we're looking at phosphorus. You can see the phosphorus is the lowest slat in the barrel. The water is limited to that height because of that slat, and so phosphorus is the limiting nutrient. Okay, if we add phosphorus, fertilizer or something like that, phosphorus, the barrel slat goes up, and the next most limiting nutrient comes into place, and in this case it's nitrogen. Okay, now in this slide, we're basically just talking about nitrogen and phosphorus, but if you look at all the slats in here, you have light, you have heat, you have mechanical support, organic matter, phosphorus, nitrogen, and potassium, other nutrients, water and air. These limiting characteristics are diverse. It's not just nutrients. And I put this in here to get us thinking about this issue of management. What are we in fact managing for? Now, we're talking about soil management, but whatever our goal is, in essence, is basically this barrel of water. We want this barrel of water to be a certain size. Okay? And we have a maximum size it can be, but we have limitations on that size. The management is basically taking care of these slats. Okay? Questions so far? We good for? All right. This is an experiment that Murray McBride and myself did. Okay? And this slide really, this is actually a toxicity issue. But I want to use this slide, and I'll talk about the toxicity issue in a sense, but I want to use this slide to sort of represent this. Okay? Now, what you're looking at is you're looking at lettuce. Okay? And lettuce is growing in the same type of soil. Okay? Every one of these lines represents a different treatment. Now, can you guys see the treatment line that's got some sort of effect to it? It's definitely, there's a suppressed growth here. Okay? Now, if we think about that in the sense of a barrel analogy, that suppressed growth could be one pot basically having less phosphorus in it. Okay? Everybody else has more phosphorus. Okay? And so we get this type of response. Now, in this case, it wasn't a phosphorus response. In this case, it was actually a pH response. Now, generally, when we think about management, and certainly when we start thinking about this barrel analogy, we generally think of some sort of limitation based on there's not enough of something. But this barrel analogy can certainly be flipped over where, in fact, it's not necessarily something that's not enough of, but it could be something that's there's too much of it. Okay, it could, in fact, be a toxic effect. Does that make sense? And that's, in essence, what you're seeing here. Each one of these pots basically has the same amount of material, but each one of these pots has a different pH. And in this case, we're talking about a very low pH. The pH gets low enough, and I start seeing availability of nutrients or toxic materials that are at higher levels than in these other ones. And what you're looking at here is you're looking at aluminum toxicity. Now, this was an experiment about lead. As the pH of a soil goes down, lead becomes more and more soluble. And our experiment was basically to take a look and see what was going on with plant uptake in lead. But we lowered the pH enough that we're looking at different responses. This is not a lead response. This is a response to an abundance of aluminum because of the lowering of the pH. It increased the solubility of the aluminum. The aluminum went into the soil solution. The aluminum then started affecting the plant roots, and you had the toxic effect, and you had the plant suppression. Does that make sense? Okay. Now, segueing this a little bit, let's think about what happens to those plants to other organisms. Now, obviously, we eat plants, or organisms that we eat plants. Okay? It turns out, if we go back to this barrel analogy, these types of plants may be, this is the amount of water in here is the plant that we're growing, and we're feeding that water, the plant, to organisms. Now, it's important to remember that not all organisms have the same nutrient requirements than everybody else. In fact, some plants have very different nutrient requirements than other plants. So if we're thinking about this from a management and use, it turns out that non-deficient plants that have the optimum resources that they need, can in fact provide deficient diets to us. We have very different requirement nutrient-wise than plants do. So even though the plant is growing at an optimum level, it doesn't mean that it's going to provide the nutrients that we need. We see this especially with things like molybdenum, selenium, cobalt, copper, phosphorus, sodium, the whole list. But in essence, you got to think about what you're growing, what you're managing it for, and where it's going to. Okay? Plants can contain high levels, even toxic concentrations of essential or non-essential elements that could be in fact toxic to them and not toxic to the organisms that are eating them. Could also be non-toxic to the plants, but in turn could be toxic to the organisms that are eating them. Okay? So you got to think about this barrel analogy not just from the performance of the plant but also or the performance of whatever you're interested in, but also from the performance of the thing that's going to be using that plant, that barrel. Okay? Does that make sense? Okay.
This has been a production of Cornell University, on the web at cornell.edu.